Hello everyone, myself Dr. Santyamay Kundu. I welcome you all to this lecture of soft computing technique. This is the first lecture of module 5. Till now, we have discussed working principles of genetic algorithm, population set, some encoding techniques, and binary encoding and decoding techniques in module 4. In this class, we will try to understand the selection operator. So, the introduction to selection operator in genetic algorithm. So, in genetic algorithm, the selection operator plays a crucial role in the process of evolution, where it is responsible for choosing individuals, that is, solutions from the current population to create offspring for the next generation. The main idea behind selection is to preferentially choose individuals that have higher fitness, ensuring that better solutions have a higher probability of contributing to the next generations. Key points. Goal of the selection operator. The selection operator aims to imitate the natural process of survival of the fittest. Individuals with higher fitness values, that is better solutions, are more likely to be selected for reproduction, while less fit individuals have a lower chance. Fitness is a measure of how good a solution is in terms of the problem being solved. It can be represented as a numerical value where higher fitness corresponds to better performance. Reproduction. The selected individual will undergo genetic operations like crossover, that is recombinations, and mutation to produce new individuals or offspring. The selection operator determines the selection operator determines which individual will participate in this process. So, types of selection methods. First one is roulette wheel selections, that is fitness proportional selections. In this method, individuals are selected based on their relative fitness. Imagine a roulette wheel where each individual is assigned a slice of proportional to their fitness. The more fit an individual is, the larger their slice will be. We'll have some numerical discussions on all these methods. A spin of the wheel determines which individual is selected. This method gives individuals with higher fitness a greater chance of being selected, but they are not guaranteed to be chosen every time. Tournament selections. So, a set of individuals, the tournament is randomly chosen from the populations. The individual with the highest fitness in the tournament wins and is selected to reproduce. Tournament selection is simply and can be adjusted by changing the size of the tournament. So larger tournaments increase selection pressure. So we'll discuss the term selection pressure, etc. Rank selection. In this method, individuals are ranked according to their fitness. The selection probability is then based on this rank rather than the raw fitness values. Rank selection is useful Rank selection is useful when there is a large difference in fitness values across individuals to avoid premature convergence due to highly dominant individual. Elitism, although technically not a standard selection method, elitism is a strategy that can be combined with other selection methods. In elitism, the best individual, usually the top few, are directly copied into the next generation, ensuring that the quality of solution does not degrade. Now, selection pressure and population diversity in genetic algorithms. In genetic algorithm, the selection pressure and population diversity are two critical concepts that directly influence the evolution of solutions. Both factors must be carefully balanced to achieve optimal performance, ensuring that the algorithm converges toward the best solution without getting stuck in suboptimal solutions, that is local optimum, or losing valuable genetic variety. Selection pressure. The selection pressure refers to the intensity with which individuals with higher fitness are favored are favored for reproduction. In simpler terms, it describes how strongly the algorithm prioritizes the selection of better solution from the current populations. High selection pressure. So meaning is that high selection pressure occurs when individuals with significantly higher fitness have a much greater chance of being selected for reproduction than those with lower fitness. Effects. So this can speed up convergence toward a solution because the fitness individuals are likely to contribute more offspring. However, excessive selection pressure can lead to a premature convergence where the population becomes too homogeneous too quickly and the algorithm may get stuck in a local optima, failing to explore the entire search space. For example, in roulette wheel selections, a large difference in fitness values between individual results in a few individuals being selected repeatedly, which can reduce diversity. Now, low selection pressure. Low selection pressure means there is a less emphasis of selecting the fitness individuals and even weaker individual may have a chance to reproduce. Effects. This encourages this encourages this encourages this encourages greater diversity in population since a wider variety of individuals contribute to the next generations. However, it can slow down convergence because less fit individuals are also allowed to reproduce, potentially leading to suboptimal solutions taking longer to emerge. Example, in roulette wheel selection with a small tournament size, all individuals have example in tournament selection with small tournament size, all individuals have a more equal chance of being selected, which reduce a bias towards high fitness individual. Second one is population diversity. Second one is population diversity. Population diversity refers to the variety of different solutions or genetic material that is individual represents in the populations. Maintaining diversity is essential for a genetic algorithm because it allows the algorithm to explore a wider search space and reduce the risk of premature convergence to suboptimal solutions. Importance of diversity exploration. Diversity ensures the algorithm does not quickly converge to a local optimum but continues to explore new areas of the solution space. Avoiding premature convergence. If a population becomes too uniform, that is lacks of diversity, the algorithm will stop exploring new solutions and may converge to suboptimal or local solutions. Effects of low diversity. Convergence to local optima. If there is insufficient diversity, the population will tend to focus one or a few areas of the search space, reducing the chances of finding the global optimum. Loss of genetic variety. With low diversity, the genetic pool becomes too narrow, making it harder for the algorithm to create beneficial mutation or combination of traits. Effects of high diversity, slower convergence. While maintaining diversity is crucial for avoiding local optima, high diversity may slow down convergence because the algorithm may waste resource exploring less promising areas of the search space. High diversity allows the algorithm to explore the search space better, but it can sometimes reduce the algorithm's ability to exploit promising solution effectively. So the key of an effective genetic algorithm is balancing selection pressure and population diversity to ensure both sufficient explorations of the search space and the gradual convergence of optimal solutions. Here are some strategies to manage this balance. Elitism. So elitism is a strategy that involves directly copying the best individual to the next generation. This ensures that the best solutions are never lost due to genetic operations, maintaining high fitness levels in the population while still allowing for exploration. Adaptive selection pressures. In some cases, it is beneficial to adjust the selection pressure over time. Early in the algorithm, Early in the algorithm's executions, a lower selection pressure might be used to encourage explorations, while later in the run, higher selection pressure can drive the algorithm to focus on fine tuning the best solutions. Mutation and mutation introduce random changes into individual. While mutation introduce random changes into individuals, which helps maintain diversity in the populations. Even if selection pressure favors a narrow set of solutions, mutation can reintroduce variety, potentially rescuing the population from premature convergence. Crowding and niche. This technique encourages the maintenance of multiple subpopulations or niches within the overall population. Each potentially focuses on different areas of the search space. By protecting diverse solutions, these techniques help prevent the population from becoming too homogeneous. Tournament size. Adjusting the tournament size in tournament selection can impact the selection pressures. A smaller tournament size will result in more individuals having a chance of being selected, thereby reducing selection pressure and maintain diversity. Larger tournament sizes increase selection pressures, making the fittest individual more likely to reproduce. The relationship between selection pressure and population diversity is crucial in genetic algorithms. Too much selection pressure can cause premature convergence, while too little can slow progress. Maintaining a balanced population diversity allows the algorithm to continue exploring the population space effectively while gradually converging toward high quality solutions. By carefully tuning these parameters, a genetic algorithm can perform more efficiently and effectively, avoiding common pitfalls like local optima and stagnation. Exploring and exploitation in genetic algorithms. In genetic algorithms, the term explorations and exploitations refer to essential components of the search process. Exploration refers to the ability of the algorithm to search through a broad range of potential solutions in the problem space, discovering new areas that may contain better solutions. Exploitation refers to the process of focusing the search on areas of the solution space and that are known to contain good solutions, refining and improving upon them. Both exploration and exploitation are critical for success of a genetic algorithm. The key challenges is to balance these two aspects effectively to find optimal solution without getting trapped in suboptimal regions, that is local optima, or missing the best solution altogether. The exploration in genetic algorithm. Exploration refers to the algorithm ability to discover new regions of the search space. During exploration, the algorithm is trying to avoid converging too quickly to a solution, allowing it to investigate a wider array of potential solutions. Why exploration is important? That is, first one is that avoiding local optima. Without sufficient exploration, the genetic algorithm might converge prematurely on a local optimum, that is a solution that is good but not the best, rather than finding a global optimum. Maintaining genetic diversity. Exploration helps maintain diversity in the population, preventing the entire population from becoming too similar to each other, that is, too much exploitation of a particular region of the solution space. Introducing novel solutions, exploration allows the algorithm to discover new, potentially better solutions that were not considered in earlier generations. How exploration is encouraged? First is the mutation. Random mutation in the genetic code of individuals allow the algorithm to explore areas of the solution space that would otherwise be missed by crossover alone. Mutation introduce randomness which keeps the population from becoming stuck in one part of the search space. Low selection pressures. By applying low selection pressures, the algorithm is more likely to select a diverse set of individuals from different parts of the search space, encouraging exploration of these areas. Diverse initial populations. A diverse starting populations ensure a broader search area in the beginning of the algorithms. execution. Now, exploitation in genetic algorithms. Exploitations, on the other hand, refers to the algorithm focus on refining and improving solutions that are already known to be good. In this phase, the algorithm tries to fine tune the existing solutions, building upon the successful characteristics of better performing individuals. Why exploration is important? That is, first is convergence. Algorithm has explored, Once the algorithm has explored a sufficient portion of the search space, exploitation ensures that the population converges towards an optimal or near optimal solutions. Refining good solutions, exploiting successful solutions through operation like crossover, that is combining good traits of individuals and selections prioritize high fitness individual, refines the solution and leads to higher quality offspring. How exploitation is encouraged? High selection pressure. First one is, high selection pressure ensures that the fittest individual have a higher chance of being selected for reproduction, which promotes the propagation of good solutions. This helps the algorithm focus on improving the best solution found so far. Or recombination is a key operator that allows the algorithm to exploit successfully genetic combinations. By combining the genetic material of high fitness individuals, the algorithm can generate offspring that are expected to perform well. Elitism. Elitism ensures that the best individual from the current generation are directly passed on to the next generation, ensuring that the quality of solution does not deteriorate over generations. Factor effective exploration and exploitation. First one is selection pressures. High selection pressure favors exploitation because it selects individual based on fitness, which may reduce diversity in the population, pushing the algorithm towards a local optimum. Low selection pressures favors the exploitation because it allows a broader range of individuals to be selected for reproduction and promoting diversity in the populations. Crossover and mutation. Crossover encourage exploitation by recombining good solution genes to create potentially better offspring. Mutation encourage exploration by introducing randomness into the populations, helping the algorithm discover new solutions that might not be reached through crossover alone. Population size. A large population tends to support exploitation more effectively because it maintains more diversity, allows the search to cover broader area of the solution space. A smaller population may converge more quickly but might not explore the solution space as thoroughly. Gener- Generational elitism. Elitism guarantees that the best individuals survive and reproduce, thus supporting exploration. However, if too many elite individuals are carried over into the next generation, exploration can be hindered. Exploration can be hindered. The key challenges in genetic algorithm and many other optimization algorithms is finding a balance between exploitation and exploitation. If the algorithm focuses too much on exploitation, it may quickly converge to a solution without fully exploring other promising areas of the search space. This can lead to premature convergence and being stuck in a local optimum. On the other hand, if the algorithm focuses too much on exploration, it may never settle on any particular solution and the search might become inefficient. The algorithm might waste computational resources on suboptimal regions of the search space and slow or incomplete convergence can occur. So, the population diversity. So, this is similar to the concept of exploration. The population diversity means that the genes from the already discovered good individuals are exploited while permitting the new area of search space continue to be explored. And selection process, so this is the similar to the concept of exploitation. It is defined as the degree to which the better individual are favored. These two factors are inversely related to each other in the sense that if the selection pressure increases, the population diversity decreases and vice versa. Thus, if the selection pressure is high, the search focuses on a good individuals in terms of fitness of the at the moment. It loses the population diversity. Higher rate of convergence often leads to premature convergence of the solution to suboptimal solutions. Now, if the selection pressure is low, may not be able to drive the surge properly, and subsequently the stagnation may occur. The conversion rate is low and the genetic algorithm take unnecessary long time to find optimal solutions. Accuracy of solution increases as more genes are usually explored in the search if the selection pressure is low. Now we have discussed few selection technique, that is roulette wheel selections, rank selection, tournament selection, and steady state selections. So now there is the comparison of the different selection strategy in terms of population diversity and selection pressures. So roulette wheel selections, it works fine when the fitness values are uniformly distributed. This is low population diversity. It is high with selection pressures. Rank selections. It works fine when the fitness values are not necessarily uniformly distributed. There is high population diversity and selection pressure is low. Tournament selection, it works fine when the population are with very diverse set fitness values. Population diversity is moderate. It provides high, it provides very high selection pressures. Steady state selections. Population diversity is decreases gradually as the generation advances, as selection pressure is too low. So that is the comparison between the all selection schemes in terms of population diversity and selection pressures. So in this class we have understood few terms which are which are population diversity, we have understood selection pressures, we have understood explorations, we have understood exploitations. So please try to understand these terms: population diversity, selection pressure, exploration, and exploitations. So next class we will study some numerical example of selection procedures. So these are the references for today's class. Thank you.